given two square matrices, we are going to say that they are similar if one of them can be written as the other one multiplied in two sides by a matrix and its inverse. Given our matrix, if we multiply it by an invertible matrix and its inverse, so the matrix obtained is going to be called similar. So this matrix and this matrix are similar matrices. If we had a particular case that when we do that, this matrix that we obtain this is actually diagonal, meaning has entries only in the diagonal and everywhere else is a zero, we will say that our matrix is diagonalizable. So, in order to be diagonalizable, a matrix have to exist some matrix P such that when we multiply after and before, we obtain a matrix that is diagonal. So the relation between similar matrices, the relation between this matrix and this matrix is a very important one, since in the case that the matrices are related by similarity, so then they conserve certain properties. So we have that is a matrix is obtained as another matrix multiplied by a matrix and its inverse. So if this matrix has certain determinant, this matrix will have the same determinant. So the determinant is a property that is invariant under similarity, which means that if two matrices are similar, then they have the same determinant. Also, if we have that this matrix is invertible, so then this matrix is also invertible. Trace, the rank, the nullity, all these things coincide. So the nullity of this matrix will coincide with the nullity of this one. The characteristic polynomial will also coincide. The characteristic polynomial of this matrix will coincide with the one of this one. And finally, a very important property that is conserved by similarity is that the eigenvalues of this matrix are the same as the eigenvalues of the other matrix. So essentially, the idea is that, as we said before, so matrices are similar if they are related by this formula, and in case that the result matrix here is diagonal, we are going to say that this matrix is diagonalizable. So the matrices that are diagonalizable are very important matrices, since doing any operation with a matrix that is diagonal is much easier than doing that operation with any other matrix. Let's study when a matrix is diagonalizable. So not all the matrices are going to be diagonalizable. Some of them are going to be and some others not. So let's study when a matrix is actually diagonalizable. In order to study that, we have this result, this theorem, that tells us that a matrix is diagonalizable only in the case that the matrix has n linearly independent eigenvectors. So essentially, what this thing is saying, since in this case those vectors form a basis of Rn, so the matrix will be diagonalizable only in case that Rn has a basis formed only by eigenvectors. So we have then a condition. So this is going to be the condition. That's what we have to investigate. If we are able to find a basis of eigenvectors, so then it's going to be diagonalizable. Otherwise, it's not. These basic eigenvectors are going to be the columns of the matrix P. Remember that the idea was that A is diagonalizable if there exists a matrix P such that we multiply here and we multiply here by the inverse, and the result is a diagonal matrix. Well, we are saying now that that will happen when we can find a basis of eigenvectors. And moreover, what this result is saying here is that the matrix P for the diagonalization is obtained by writing that base as columns of it. So the matrix P is going to be a matrix in which the columns that we write here are going to be the eigenvectors in the bases. Moreover, the result matrix, the diagonal matrix, is going to be a matrix whose entries in the diagonal are going to be exactly the eigenvalues corresponding to these eigenvectors. So, with this result, we have not only said how we are going to decide if a matrix is diagonalizable or not, but also the result tells us what are the matrices that give us the diagonal form. So the matrix P is then the matrix whose columns are the vectors, the eigenvectors of the base. And the diagonal matrix is a matrix that will have in the diagonal the eigenvalues. The eigenvalues corresponding to the eigenvectors in the base. This result will allow us to actually construct the basis with eigenvectors. This result says that if we have k different eigenvalues, so observe here all the things included there. First, they are k, so that means any number, right? So it's not related to the dimension of the matrix. So what this result says is that if we have any number of distinct eigenvalues, so what happens is that the eigenvectors corresponding to these eigenvalues are going to be always linearly independent. So this is a very important result that tells us what is the relation between the vectors in different eigenspaces, because you see that if they correspond to different eigenvalues are going to be in different eigenspaces. So suppose, for instance, that we have a matrix that is n by n. And suppose that we have k different eigenvalues. So that will be, for instance, the eigenvalue lambda 1, lambda 2, until lambda k. And so for each of these eigenvalues, we will have a set of eigenvectors, right? So the eigenvectors corresponding to that eigenspace. So for this one, we will have another base, and for this one, we will have another base. So what this result is saying is that if we pick a vector here, and a vector here, these vectors are going to be linearly independent. Now, putting that together with the fact that the vectors here between them are linearly independent, because this is a basis of the eigenspace, this one between them are linearly independent, and this one are linearly independent. What this thing is saying is that the whole lot here, all this thing, is going to be linearly independent. So essentially, if we want to have a base, all what we want, once that we calculate the bases of each of the eigenspaces, we want that when we count them all, they actually are n, right? So because our matrix is n by n. If we manage to get that, if we manage to get as many eigenvectors as the dimension of the matrix, so then the matrix is going to be diagonalizable. One case in which this is guaranteed will be in case that we don't have really that many here. So in case that we have directly here n eigenvalues. If that will be the case, so if A have n distinct eigenvalues, so then A is diagonalizable directly, because then we'll have for each one of the eigenvalues, we will have one eigenvector, and then we will have in total n eigenvectors, which will make a basis, and so then the matrix will be diagonalizable. So the first step will be find the eigenvalues. So we will find the determinant of A minus lambda identity equal to 0, and that will give us the list of eigenvalues for the matrix. Once that we have the list of eigenvalues, we are going to find the basis for each eigenspace. So in order to do that, we take the first of the eigenvalues and we calculate the eigenspace, that is the kerr of A minus lambda 1 I. We calculate the basis of this space. So let's say that we obtain certain number of vectors as basis of that one. And then we do that for all the eigenspaces until the last one corresponding to the last eigenvector, we get some other eigenvectors in the base. So once that we have all these eigenvectors here, the next step is count the total of eigenvectors. So just count how many we have here. If the number happens to be n, happens to be the dimension of the matrix, so the matrix is diagonalizable. Otherwise, it's not. So let's consider an example. So let's consider this particular matrix, the matrix 6 minus 1, 2, 3. And so we're going to start by finding, in order to decide if this matrix is diagonalizable or not, we are going to start by finding the eigenvalues. So to find the eigenvalues, we calculate the determinant of A minus lambda by the identity, which means the determinant of, and we take this matrix and we just subtract lambda in the diagonal. That's all what we do, right? 6 minus lambda minus 1, 2, 3 minus lambda. So the determinant of this matrix. So let's calculate this determinant. In this case, it's a 2 by 2 matrix, so that will be just this minus this. So let's do this operation. This will be, in this case, 6 minus lambda times 3 minus lambda minus 2 times minus 1, which is plus 2. So by doing the operations here, we do distributive here, we get 18 minus 6 lambda minus 3 lambda plus lambda square plus 2. Let's combine like terms here, and we get that this is equal to lambda square minus 9 lambda plus 20. And now we want to calculate the zeros of this, right? The characteristic equation. So we put this equal 0. So from here we get that lambda is equal to 9 plus minus the root of 81 minus 80 divided by 2. So that makes lambda equal 9 plus minus 1 over 2, right? So that is 9 and 1 is 10, over 2 is 5, and 9 minus 1 is 8, over 2 is 4. So in this step 1, we found the eigenvalues are 5 and 4. Okay, so that's the result of the first step, finding eigenvalues. We found that these two eigenvalues are going to be 5 and 4. So let's write down just the result of this part here. So let's write down then that the two eigenvalues here are lambda 1 equal 5 and lambda 2 equal 4. These are the eigenvalues. And now in the second step, we need to calculate the basis for each eigenspace. So let's start calculating each of the eigenspaces. So the first one, the one corresponding of lambda 1 equals 5, that means that we need to calculate the kerr of A minus 5 times the identity. And that means the matrix, so is this matrix, well, the one that we have written before with the lambdas, right? So we have written before, I erased it, this was 6 minus lambda minus 1, 2, 3 minus lambda. So this is the matrix in which we have to substitute by the concrete values of lambda. So in this case, we are substituting by lambda equal 5. So we put a 5 here, will be 6 minus 5 is 1, minus 1, 2, and here 3 minus 5 is minus 2. So this is the matrix that multiplied by xy should be equal to 0, 0. That's the definition of the curve. And now we do the Gauss-Jordan elimination, and so we reduce this matrix here by doing this reduction. We get here that by just multiplying the first row by minus 2 and adding to the second, we get here that the reduction is 1 minus 1, 0, 0, right? xy equal 0, 0. And that means then by multiplying this by this now, that means x minus y equals 0. So now we can put y as a parameter, is y is equal t. From here we get that x is equal y, so x is equal t. So that means that our vector is going to be, the xy is going to be t. So we take t as a common factor, and in that way we extract the base, and the base is in this case 1, 1. So we got then the first of the bases of each eigenspace, we got the basis for the first one. I mean, for the eigenspace corresponding to this, we got that the basis is this vector, the vector 1, 1. So let me write down again the data that we found. The data is that the basis here that we were looking for is the basis formed in this case just by one vector, right? So the vector 1, 1. So this is the basis then for this eigenspace. And so we should do the same, exactly the same for the other eigenspace. So for the other eigenspace, we have to do exactly the same. So we said lambda 2 equals 4, right? So equal 4. So we need to calculate now the curve of a minus 4 times the identity. And we do exactly the same. I mean, we just write the matrix now, but putting here instead of lambda just the number 4. And so it will be 6 minus 4 is 2, minus 1, 2, and 3 minus 4 is minus 1. So this is the matrix. By doing the reduction, so we can see clearly that in this case the reduction gives us 2 minus 1, 0, 0, right? We can reduce more if we want to just leave it like that so we don't deal with fractions. So this is the matrix reduced. And so when we multiply this matrix by xy, we get 2x minus y equals 0. And so we get from here that y is equal to x. If we put x equal t, the parameter, so y is equal to t. And so our vector is going to be, t to t. We take t as a common factor, and then it's going to be 1, 2. So the basis here is going to be just the vector 1, 2. And so the basis here is going to be just the vector 1, 2. In that way, we finish the step number 2. We found a basis for each of the eigenspaces. So the first eigenspaces, the first eigenspace is spanned and has basis the vector 1, 1, and this other eigenspace has basis 1, 2. So we have the basis for each of the eigenspaces. Okay, so then let's just go directly to the last step, that is just a step of checking, right? So the last step, what says is that we need to just count the total number of the eigenvectors that we got, count them. Well, 1, 2, easy to count here, right? So there are 2. and now check if this number happens to be the dimension of our matrix. And it is, right? So this matrix is 2 by 2, so we are in R2. So we got exactly 2 eigenvectors, so that means that our matrix is diagonalizable. Okay? So this matrix then, so we can say that this matrix then is. Okay, so that's a way then to determine if a matrix is diagonalizable or not. So finding the eigenvalues, finding the bases for each eigenspace, count all the vectors in the bases. If the number of vectors coincides with the dimension of the matrix, so then the matrix will be diagonalizable. Okay, and in that case, when it's diagonalizable, we have calculated here most of the data that we are going to actually need for actually calculating what is the diagonal form of this matrix. Okay, so let's see in the next step then how to actually diagonalize a matrix. I mean, how to find the diagonal matrix that is similar to the matrix given. First, let's review the steps. What we need to do is first determine if the matrix is diagonalizable, because otherwise we cannot find the diagonal matrix, right? So first we should determine if the matrix is diagonalizable by just doing what I just explained. But then once that we know that the matrix is diagonalizable, the thing is that we have almost everything done, because in the next step says form the matrix P with the basic eigenvectors as columns. So whatever eigenvectors we were counting that they were in, so we just now put them as columns, and that is what the matrix P is going to be. Then after we write down the matrix P in that way, just writing the eigenvectors as columns, then we are going to calculate the inverse matrix. And once that you have a concrete matrix P, the calculation of the inverse matrix you do by any of the methods you know of calculating inverse matrices. And then once that you have the matrix P and the matrix P minus 1, then you have to form the matrix D, the actual diagonal matrix. And this matrix is going to be formed by putting in the diagonal entries the eigenvalues. So the eigenvalues that you already calculate in the first part, those are the ones that go in the diagonal entries of the matrix D. And so then you have all the matrices that you needed, P, P minus 1, and D. What do you do with them? Well, you can multiply them, as is explained in the similarity form. And when you multiply them, you can check that this gives you actually the matrix D. Okay, so let's do all this in the concrete example that we just work on. So essentially, we have everything that we need to do the diagonalization already here. So we have already calculated everything that we need. So let's go to this step, determine if the matrix is diagonalizable. We already have done. We determined that that's correct because we find, let me write down again what the matrix that we're talking about is. The matrix was this 1, 2, 3. And so to determine if the matrix is diagonalizable, we already have done. We found that. Let me copy again the data that we calculate here. So the eigenvalues here were 5 and 4. And the basis of eigenvectors is the one given here. So let me copy those again. The basis for the eigenspace here is the vector 1, 1, and the basis of this other eigenspace was the vector 1, 2. Let's check again. Yeah, 1, 1, and 1, 2. These were the vectors that we obtained in the other part. So we have determined already that this matrix is diagonalizable, and we have this data that was the data that we needed in order to determine that. And so in the next step, we have to form the matrix P. How? Well, the matrix P is going to be always a matrix of the same dimension of the matrix given, but as columns is going to have just the vectors that we found as a basis of the eigenspaces. So the first column is going to be the first vector, 1, 1, and the second column, the second vector, 1, 2. That's the way to calculate the matrix P of eigenvectors. I mean, the matrix P whose columns are the eigenvectors in the basis. So, in the next step, we need to calculate the inverse matrix of this. Well, for this, you apply any of the methods of calculating the inverse matrix, by cofactors or by doing the Gauss-Jordan transformations. In any way you choose, you will find that the inverse matrix of this one is 2 minus 1 minus 1, 1. Okay, so we have the matrix P and we have the matrix P minus 1. Now we have to form the matrix D. The matrix D is also very easy to form, since the matrix D is a diagonal matrix, means that have entries in the diagonal only, and everywhere else has zeros, right? So we can put directly that have a 0 here and a 0 here. And the entries in the diagonal, this one and this one, are going to be given by the eigenvalues. So it's going to be 5 and 4. In that order, right? Because it has to be the same order in which we put the columns here. 5, 4. Okay, so these are the three matrices that we need to have in order to diagonalize the matrix. So this is the diagonal form already of the matrix. So this matrix D is a matrix that is similar to this matrix A, meaning that it's going to share many of the properties that this matrix has, being the matrix D much easier to work with than the matrix A. Okay, and finally, once that we have all these matrices, let's check that this is correct. Let's actually do this multiplication with the matrix P and P minus 1 and the matrix A that we have given, and let's check that the result is really the matrix D. So let's multiply this matrix. I'm writing the matrix P minus 1 first, 2 minus 1 minus 1, 1. This is the matrix P minus 1, and then the matrix A. So that was the matrix, the original matrix given, the matrix 6 minus 1, 2, 3. So that was the original matrix given. And then multiply by P. So the matrix P is the one that we have here. So let's write down the matrix P, 1, 1, 1, 2. So the multiplication of this one is supposed to give the matrix C. So let's actually do the multiplication. So these are three things multiplied. We have to multiply 2 at a time. You can choose. You can associate these 2 and multiply, or you can associate these 2 and multiply first, as ever you prefer. I'm going to multiply these 2 first. So that will be 2 times 6 plus minus 1 times 2, right? So that will be the rule for multiplying here. That will give me 10. And then 2 times minus 1 plus minus 1, 3. So that will give me minus 5, minus 4, and 4. So that's the multiplication of these 2. And still multiplying by 1, 1, 1, 2. So let's do this last multiplication here. This times this. So that will be 10 minus 5 is 5. And so 10 minus 10 is 0. Minus 4 plus 4, 0. And so minus 4 plus 8 is 4. Okay, that's the result. And we check, and it happens that it was exactly the matrix D. So the result is really the matrix D. That completes the check. We will see now how to apply diagonalization to the calculation of a power of a matrix. So if we have given a matrix A, how to calculate any power of a matrix A. Observe that the calculation of a power of a matrix, let's say we want to do 6 minus 1 to 3, the previous matrix, we want to calculate the power fourth, for instance. So what would we need to do? Well, we need to get this matrix, multiply by itself, and multiply by itself, and multiply by itself, where each of these things involve a multiplication of matrices, right? So that will be a very long process to do directly the power of a matrix. Well, in case that the matrix is diagonalizable, so we're going to have that this process is much simpler. When a matrix is diagonalizable, so we have that the matrix multiplied by a matrix P and its inverse gives a diagonal matrix, right? That's what it means to be diagonalizable. But then in this case, we can solve for A by just multiply by P in the left side, making here the identity. So this is the same that multiplying by 1. So in this part, we get as AP equal PD. And then we can multiply by P minus 1 in the right, and so we obtain the same thing here, the identity, that is like multiplying by 1, and so we get just that A is equal PDP minus 1. So every time that a matrix is diagonalizable can be also be written in this way, as a product of a diagonal matrix with a matrix here and its inverse. Well, we can use this form of the matrix A, writing as P, D, P to the minus 1. And so when we do the power K of this matrix, we can observe that the matrix P and P minus 1 are going to be all cancelled in each power, and the power ends up only in the diagonal matrix. So this formula gave us a really easy way to calculate powers, because what it says is that to calculate the power of a matrix, that will be a complicated and long operation of multiplying the matrix by itself, reduced to multiply only the power of the diagonal by P and P minus 1. And the power of the diagonal is much easier to do because consists in only doing the power of the entries in the diagonal. So, for instance, the matrix that we used to have, 6 minus 1, 2, 3. We know that this matrix is equal to certain matrix P that we already calculated, multiplied by the diagonal, that was this one, and multiplied by P to the minus 1. So then, to do a power of this, let's calculate the power fourth, will be only to do the power fourth in the diagonal, and doing the power fourth in the diagonal means only to do the power fourth of the diagonal entries. So then this will be P, and so 5 to the fourth power, that would be this, 0, 0, and 4 to the fourth power, that will be this. Okay, so this will be then the power fourth of this matrix. And if you want to find the final result reduced, you need to multiply actually for the matrices P and P minus 1 that we calculated before.